In this video, we are going to take a look at orthogonal bases and what's known as the Gram-Schmidt process. This is chapter 5.3, and we'll be working through examples and theorems and explanations. So our learning objectives for this chapter section are to show that a set of vectors is orthogonal and forms an orthonormal basis. So you'll learn how to show those calculations. We are going to learn how to represent a vector relative to an orthonormal basis. And you are going to learn how to apply the Gram-Schmidt orthonormalization process. So this idea of orthonormalization, that is when we have vectors that are orthogonal, and then if each vector is also a unit vector, that's what's known as being orthonormal. So that's what we're going to take a look at here in this first video. So although a vector space can have many different bases, some bases may be easier to work with than others. So for example, in R3, we have this standard basis S that for short, we call it E1, E2, E3, and that's just 1, 0, 0, 0, 1, 0, and 0, 0, 1. And two properties that make the standard basis desirable are that the vectors are already normalized. Each vector is a unit vector. And so when you do the norm of each of these E1, E2, E3, you got 1. And then the vectors are what are known as mutually orthogonal. So when you do the dot product, and remember we're in R3, so our inner product space is the dot product for the standard inner product space that we use. And so you can see here, you could say E1 dot E2, or I actually wrote out the vectors. So you can see, of course, when you dot those, you're gonna get a 0 because each element where there's a 1 is multiplied by a 0 in the other positions of the other vectors. The same if we do E1 dot E3, which I wrote out here, 1, 0, 0 dot 0, 0, 1 is going to give us a dot product of 0. And the same for E2 dot E3, which is 0, 1, 0 dotted with 0, 0, 1. So this leads us to the definitions of orthogonal and orthonormal sets. So a set of vectors in an inner product space V is orthogonal when every pair of vectors in S is orthogonal. So if you are in R, if you do the dot product, if you're in Rn, then you're going to get 0 for every possible pair of vectors. If you're in a different inner product space, you're going to use whatever inner product we're using for that inner product space. And then if in addition, each vector in the set is also a unit vector, then we say the set S is what's known as orthonormal. So for S vectors V1 through Vn here, we can look at the definition in two forms. We've got the first part, orthogonal is when your inner product is 0 for every I and j that are distinct vectors in your set. And then it's orthonormal if you have that first property that the inner product is 0 for every distinct vectors in the set, but also if you have the norm is 1 for each vector, 1 through n in the set. If S is a basis, then it's an orthogonal basis or an orthonormal basis. So it could be orthogonal if the length of the vectors is different from 1, and if you've normalized all the vectors so that they have length 1, it's an orthonormal basis. And we'll see it's really easy if you have an orthogonal basis, you know how to normalize vectors to give them length 1, so it's real easy to build an orthonormal basis. So let's take a look at an example. So we're going to use S here. So S is going to be the set of vectors cos theta, sine theta, 0, negative sine theta, cosine theta, 0, and 0, 0, 1 are what we think of as E3 and R3. And we're going to show that it's an orthonormal set. So we are in R3 here, and we're going to use the dot product. So our first calculation is to take cos theta, sine theta, 0, the first vector, dot it with the second vector, negative sine theta, cos theta, 0. So it's going to give us 0 for the last part of the dot product, and the first parts are going to be negative cosine theta, sine theta, and then the second part is going to be a positive sine theta, cos theta. So those cancel out and we get a 0. Then if you do cos theta, sine theta, 0 dotted with 0, 0, 1, of course you're going to get a 0 there because you've got zeros in the respective places. And then similarly, if you do negative sine theta, cos theta, 0 dotted with 0, 0, 1, you get 0, 0 also. And then we want to check that it's normalized. So you can verify for cos theta and sine theta, you're going to square those add them up and you're going to get 1, and then you're rooted and you're still getting a 1. For negative sine theta, well, negative sine theta squared is still just positive sine theta squared plus cosine theta squared. And that 0 squared isn't going to make a difference. So we get a 1 again, and the root of 1 is still 1. And then, of course, 0, 0, 1, the norm is just 0 squared plus 0 squared plus 1 squared. So you got a square root of 1, or just a 1 there. So to show that this is an orthonormal set, we went through both properties here for an orthonormal set. We showed the inner product was 0. In this case, the inner product is a dot product because we're in R3. And then we showed the length of the vector, the norm of the vectors, were 1 for each of the vectors. So if any one of these vectors was a different length, that would be okay to be orthogonal, but then the set wouldn't be an orthonormal set. So this brings us to theorem 5.10, and that says that orthogonal sets are linearly independent. So let's see why this is true. So what the theorem is saying is that if S is the set of vectors V1 through Vn, and it's an orthogonal set of non-zero vectors in an inner product space V, then that set S is going to be linearly independent. So what we need to show for linear independence is if the equation C1V1 plus C2V2 added all the way through CnVn is 0, that's only true if the scalars C1, C2 through Cn are all 0, so that there's no linear dependence. So to do this, we're going to form the inner product of both sides of the equation with each vector in S. So for each I, we are going to take C1 V1 plus C2 V2 plus Ci Vi in the middle. So this is some middle element. Keep adding the rest of the elements through Cn Vn. And then we're gonna inner product that with Vi. And so if we do that, we are going to get 0 vector inner producted with I. And so that tells us that if you pull C1 out of the inner product, so using our inner product properties, and then you have V1 inner product with Vi plus C2 pulled out, V2 inner product with Vi. In the middle, you've got Ci inner product with Vi and Vi plus Cn inner product Vn with Vi equals 0. So S is orthogonal, remember? So that was part of our given information. So then Vi and Vj, that's 0 for all the I's and J's that are not equal. So then that reduces us to, on the left, everything else is going to be 0 except Ci Vi dotted with itself. So that equation is going to say, well, then Ci, well, Vi inner producted or dotted if we're in R3 with itself equals 0. Okay, but each vector is non-zero. So then, well, we know the Vi inner producted with itself is not 0. That's just the norm of Vi squared, because each vector is a non-zero vector. Then we know, okay, this can't be 0. So that must mean this constant over here is the 0. So that's true for every Ci. We could go through I1 through N with this process and show that every one of these constants must be 0. And so the set must be linearly independent. That's the only way we're going to get the equation here equal to 0. So this C1V1 plus C2V2 added all the way through CnVn equals 0. We just showed only if each Ci is 0. All right, so let's do an example. So we're going to shift away from R3. We're going to head over and look at the continuous functions on 0 to 2 pi. And then we're going to define our inner product as the integral from 0 to 2 pi. So end of the interval to the beginning of the interval to the end of the interval are our bounds. And then it's the product of f of x and gx. And we saw this inner product in earlier parts of chapter 5. So we want to show that this set 1 cosine x, sine x, cosine 2x, sine 2x, all the way through cosine nx, sine nx is a linearly independent orthogonal set. All right, so we use software to integrate the following expressions, and then we're going to use identities here. So if you check your calculus book also, you'll remember that some of these formulas we're going to see are those same formulas from the tables of integrals that you studied probably in second semester calculus. So in our examples, you can double check my calculations on Wolfram Alpha or other software or graphing calculator if you use that. Or you can go look up those integral tables to see how these formulas came about. I'm not going to work through them because you all completed calculus to get to this point. So you can look back at your calculus notes or check in with me during office hours if you have questions. So if we look first at the inner product of 1 and then sine of nx, we're going to make use of the fact that if k is an integer, sine 2 pi k is going to be 0 and cos of 2 pi k is going to be 1. We know those are the starting points for the sine and cosine functions. Sine starts at 0, cosine starts at 1. And then they're cyclical with period 2 pi. So the inner product of 1 and sine of nx is going to be the integral from 0 to 2 pi of 1 multiplied by sine nx. And then from software or our tables at the back of the calculus book, we know the integral of sine nx is going to be cosine, negative cosine nx divided by n. You could also do a u substitution here and get the same result. And then this is from 0 to 2 pi. So using the fact that cosine of 2 pi n is going to be 1, we get here negative 1 over n plus 1 over n. So we get the plus because we're subtracting a negative. And so those cancel each other out. So that's going to be a 0. Now remember, we're trying to show that this is a linearly independent orthogonal set. So our goal here is to show that all of these inner products are zeros. So let's go on to the next inner product. That's 1 inner producted with cosine nx. So what we're doing is we're taking care of all of the ones with every possible combination of cosine and sine, where n is this arbitrary value from 1 to n in this case. Okay, so 0 to 2 pi is going to be our bounds here of the integral. And then we're going to have 1 times cosine nx, or just cosine nx. So we know from u substitution, the integral of cosine nx is going to be sine nx over n, evaluated from 0 to 2 pi. Well, those are just zeros, so we get a 0 here. All right, now let's take a look at if we do a sine of mx interproducted with a sine of nx, because remember, we're thinking every combination of vectors here. And then we'll also take a look at cosines interproducted with each other and the cosine and the sine interproducted with each other when m and n are different and when n is the same value there. Okay, so sine interproducted with itself when m is not n. So these are 2 different sine vectors in this set. So from our formulas, we know that this is going to be sine of m minus nx over 2m minus n minus sine of m plus nx over 2m plus n. And again, you can find this formula in the back of a calculus book, or you could plug in some values and run it in Wolfram Alpha to verify. And so if we're evaluating from 0 to 2 pi, well, sine at 2 pi is just zeros. So we get all zeros here. Now, if we shift over to the cosine, the formula for cosine, integrated cosine of mx and cosine of nx from 0 to 2 pi, well, that also integrates to sines in this form. And so we get here, again, zeros. Now let's take a look at if we've got cosine of mx and sine of nx, where m and n are different values here. So then when we integrate that product, we get this formula. Cosine of m minus nx over 2m minus n minus cosine of m plus nx over 2m plus n evaluated from 0 to 2 pi. And so when we plug these in, we're going to get some cancellations here. We know cosine at 0 and 2 pi are 1s. So we get 1 over 2m minus n minus 1 over 2m plus n. And then we're going to subtract what actually ends up just being the opposites of those. So we get cancellation and a 0 here. And then our last calculation to verify down here is cosine of nx and sine of nx if n is the same value. And so that's going to give us a negative cos squared of nx. So you could also just plug n in for m and n in the formula we just worked out above to see how this comes out to be. And so we're going to get negative 1 over 2n plus 1 over 2n, which cancels out, and another 0. So we just showed here that every combination gives us a orthogonal set because all of the inner products are 0. And so this is going to be linearly independent based on theorem 5.10 that we just proved. So because each vector is orthogonal to the other one, it's an orthogonal set of non-zero vectors. So then we get that it's also a linearly independent set. All right, so from that theorem and then theorem 4.12 that I put down here to remind you, we get that corollary that if V is an inner product space of dimension n, then any orthogonal set of n non-zero vectors is going to be a basis for V. So we get the linear independence part from theorem 5.10 that we just showed. And then recall theorem 4.12 that I pasted down here. That tells us V is a vector space. And then if vectors V1 through Vn is a linear independent set of vectors, then it's also a basis. So that's where the basis part comes from. So we show the linear independence with theorem 5.10, and then we already showed back in chapter 4 that a linearly independent set of vectors in V is a basis. All right, let's look at one more example here. So we're going to look at this set S of vectors here in R4. So we got 0, 1, 0, 1, negative 1, negative 1, 2, 1, 2, negative 1, 0, 1, and 2, 2, 3, negative 2. And we're going to show that this is an orthogonal basis of R4. All right, so we have to show here that it's orthogonal between each pair of vectors. And then if we can show that by theorem 5.10's corollary, if we've got an inner product space, yeah, we have R4 plus the dot product, so it's our inner product space, then any orthogonal vet of n non-zero vectors is going to be a basis. So if we can show that these are all orthogonal to one another, then we get a basis out. And you can check here when we go through the dot products. Each value here works out to be a 0. If you want to pause and double check my calculations, you could stop here and pause and verify all of these cancel out and give us zeros for the dot product. So then by the corollary, we get to say that this set S is an orthogonal basis for R4. All right, in the next video, we are going to continue and look at how coordinates are relative to an orthonormal basis.